So, in this video we will explain Frobenius method to solve a second order linear homogeneous equation when 0 is a singular point, that is a regular singular point. Okay. When 0 is a regular singular point, the equation is much similar to Euler-Cauchy equation. So, we will explain. So, we will just take the equation. So, how it works, a naught of x y double dash plus a1 of x y dash plus a2 of x y equal to 0. So, this is the equation. 0 is a singular point. So, that means with a naught of x equal to 0 at x equal to 0. Okay. Assume that 0 is the singular point. So, once you divide it, this is equivalent to y double dash plus a1 by a naught, a1 x by a naught y dash plus a2 x by a naught of x y equal to 0. Okay. So, because at x equal to 0 you divided it. So, you have a problem, this has a singularity, this has a singularity. So, this is defined either x is positive or x is negative, but not at x equal to 0. Okay. And this is your function p and this is your function q. So, you have a y double dash plus px y dash plus qx y equal to 0. So, this is your qx and this is your px. So, px is having singularity at x equal to 0, qx is having singularity at y equal to x at x equal to 0. So, both are not defined at x equal to 0. So, the equivalent equation y double dash plus px y dash plus qx y equal to 0, which is defined as a positive or negative. 0 it is not defined, but this is like px is having a power series representation which is maximum allowed to have 1 by x singularity. So, this is maximum, it is like something like order of 1 by x. So, this should be order of 1 by x, that is same as saying. So, px is having some power series, some constant times c minus 1 by x plus c0 plus c1 x and so on. So, that is the representation for px. Similarly, qx, which is of order of 1 by x square, is maximum, you are allowing it to of order 1 by x square. So, that means if you write qx as a power series, and this will become c minus 2 by x square, some, okay, some it is not same c, you can say some d minus 2 by x square, d minus 1 by x plus d naught plus d1 x and so on. So, this is what is the representation for x positive or x negative. So, assume that there is no other singularity. If you have a singularity, so clearly 0 is the singular point. If you have a singular point somewhere here or somewhere here, if you have, and the minimum distance either from here 0 to this point or this point, whichever is the minimum, call this some distance d1 and d2, okay, some m1. So, alpha 1 is the distance, alpha 2 is the distance here between this. Okay. So, whichever is the minimum of alpha 1, alpha 2, you call it alpha. So, that is where it is defined. So, alpha is 0 between, so mod x less than alpha. So, if you have a singular points at some points alpha 1, alpha 2, then the minimum of alpha 1, alpha 2, that is where this is defined. If there is no other singularity, you simply can have mod x is no, you should write 0 to less than mod x less than alpha. So, within this, okay. So, that is say something like x is between it is minus alpha 1. So, alpha 1 is minus alpha 1. So, you have alpha 1, alpha 2 minimum. So, this is positive side alpha 2, which is positive. So, you have a minus alpha less than 0 or 0 less than x less than alpha. So, when alpha there is no other singularity, alpha 1, alpha 2 are infinity. So, alpha is the minimum is infinity. So, you have x positive, x negative. So, that is how it is defined. So, when you have this pq, when you have this this order, when p and q are having this power series representation with maximum, you are allowed to have only 1 by x order, this is 1 by x square. Then we can apply this Frobenius method because assume that all these things, assume that Px, you can see that Px will become C1, assume that C minus 1 is 1 by x or constant by x, all these terms are 0. Similarly, all these terms are 0. Assume that such a P and Q. Then what you have is y double dash plus C minus 1 by x y dash plus d minus 2 by x square y double dash y equal to 0. So, this is exactly the Cauchy-Euler equation. So, what are the solutions? So, you know that the solutions are solutions of Euler-Cauchy. This is actually Euler-Cauchy equation, which you have studied already. Okay. So, solutions of the form we have already seen by converting x into z. So, new independent variable z, if you bring in by the transformation z equal to log x. So, what you have is e power some k z are the solutions. Okay. If you use this transformation, the equation becomes equation with constant coefficients. Then you look for solutions of the form y z as in this form. So, that will give you y x as z equal to log x. If you put, this is simply x power k. So, k is some constant. K is some constant. So, k can be even complex number. So, you do not know exactly what to do. So, k is a scalar. So, you have solutions of this form x power k for this Euler-Cauchy equation. Okay. K is a scalar. That is what we have seen. But if you have Px and Qx is also having this representation remaining. So, it is not really 1 by x square, then so it is like you are bringing out the singularity. So, you have x power k, k can be even negative, k can be anything. Okay. So, you bring this kind of solutions you bring out. So, you have a singular point, but it is regular. That means you maximum allow Px is of this type, Qx is of this type. So, what you do is instead of looking for the solutions of the given equation as a power series, which is n is from 0 to infinity, Cn x power n. Okay. Instead of this, you bring this. So, you can look for in this fashion, but you multiply with x power some r, let us say some k. So, the same k I can use some k. Okay. So, I brought this singularity part outside x power k. So, you can see that this, if I look for solutions of this form, this power series is actually finite at every point, even at x equal to 0. Only part is x power k. If k is negative, when you have a singular point, k will always be some kind of negative. So, you do not know. Sometimes even if it is a singular point, you may have k equal to 0, for some k power positive k, you may have solutions. Okay. So, this equation, when you look for x power k sigma c n x power n, what you look for, so in the Frobenius method, you look for solutions of this form. Okay. Why? Because there is a singularity, that singular part as though as k is unknown, okay, where k is unknown, unknown scalar, and Cn's are unknowns as usual. Okay, unknown scalars. So, what we did is we brought out this singular part x as x power k, and then you multiply this as a power series solution. So, this is on par with the Euler-Cauchy equation. There you x power k some constant is that is how you look for solutions, okay, for the homogeneous equation. So, because this works, actually if you take in this form, it works. That is called Frobenius method. We will see, we will demonstrate it with an example. So, what we do is we always look for solutions of this form whenever you have an equation, this one with p and q of this form. So, maximum when you have a singular part. So, when you have a singular point, x equal to singular point, you have seen already when it is regular, x into px as limit x goes to 0. This limit will be finite. As you can see, if I multiply x into px, and what you have is c minus 1 and c naught x plus c1 x square and so on. As limit x goes to 0, this will be simply c minus 1. Okay, this is actually c minus 1. Similarly, when you have this one x square qx, this is actually d minus 2, which is also finite. Okay, so you have x square, you multiply to qx, what is left is simply d minus 2 plus x d minus 1 plus d naught x square and so on. So, as x goes to 0, this is simply d minus 2. So, this is actually regular singular point. When you have regular singular point as 0, so this is what is the definition I gave, that is actually equivalent to saying P and Q are having this form. Okay. In such a case, you can look for always solutions like this. This is the Frobenius method. It will give you both the solutions, 2 linearly independent solutions you can get. So, I will demonstrate. You will have 3 cases. In each case, first of all, you will find what are the values of k for which you have the solutions. You will immediately find, you look for solutions in this power series and you substitute into the equation, you will find what is your k, and then you will be able to find Cn's remaining constants in the power series based on this k. Cn is based on, depending on this k value, you will have a different Cn's. Okay, that will determine 2 linearly independent solutions. So, based on the roots of this k1 and k2, so you will get two values for k. If they are repeated, that means they are same. If they are not repeated, if they are distinct roots, but the difference is integer, or the difference is non-integer. These are the 3 cases you will see. Okay, so we will have 3 cases. So, let us first substitute. Once we get that, and once we find what is that k, we will see those 3 cases. Substitute into this equation. So, we will start with. So, what we do is let us substitute. So, I start with an example. Okay. So, you will understand those 3 cases in each example. Each case you will see in each of these examples. Okay. I start with an example, in which case you will be able to find k values. You will find 2 k values for which those 2 k values are different, they are distinct, and their difference is non-integer. Okay. When they are so actually k satisfies some polynomial equation of second order. So, that is actually will give you 2 roots. Those 2 roots, if they are real, if they are distinct, the difference is non-integer. That is the case you are looking at it. Okay. And when they are complex, obviously the difference is non-integer, because it is when the 2 complex conjugate roots, when you take the difference, it actually becomes imaginary part, which is non-integer. Okay. So, these 2 cases we can cover in this example, in this type first of all. So, we start with this, I start with this first example, the difference is non-integer, roots are real. Okay. So, start with an example, give you an example. So, solve x square 2x y dash 2x y dash plus x plus 1 y dash plus y equal to 0. If you want to solve this, you can easily see at x equal to 0, 2x is 0. So, this is defined, there is no other singular point. This is a polynomial is this is only 1, which is a polynomial. So, x is equal to 0 is the only singular point. So, you have either x positive or x negative, you can look for solutions. Okay. So, in each case, if you take this one, that is one equation with this in this domain. If you want to work with here, you have to work differently. So, this is take the same equation, but x is less than 0. Okay. So, either this or this. So, let us work with positive. Okay. So, you look for, because 0 is a singular point. So, 0 is a singular point first of all, 0 is a singular point, and because x plus 1 divided by a2 divided by a1, and take this limit x goes to 0, you multiply with x, what happens? X goes, you will have half, which is finite. Okay. And now you look at a2 divided by a0 1 by 2x, you multiply with x square, take this limit, this becomes simply 0. So, which is finite. So, this implies, since these 2 limits are finite, 0 is a regular singular point. Immediately, if it is a regular, I can nicely extract the singular part outside, okay, in the method. So, I look for solution in this form. Okay. Look for a solution in the form yx equal to x power k is an unknown, and into some power series, n is from 0 to infinity, Cn x power n. Okay. So, the job is just to substitute this y dash, y double dash, you calculate and put it here. Okay. So, earlier we have seen that power series properties we have seen. Power series is actually when it is a power series, you have seen that it is actually converging uniformly. So, you can differentiate term by term. Okay. You can differentiate term by term. So, you can calculate y dash as term by term differentiation and substitute into the equation. Here also you can actually show the way if you look for solution in this form and you actually substitute, finally you see that this power series solution, once you find this constant Cn and this k, once you see that this power series is actually converging uniformly and absolutely in the, so 0 is the singular point, and if there is no singular point, x is positive, actually this power series is actually convergent uniformly and absolutely in this on any closed interval within this positive. So that means this power series is actually converging any closed interval here. Okay, that means you take any point you can cover with this open interval, closed interval. Okay, so and x positive, actually this series is convergent. So because it is uniformly convergent on any closed interval on the x positive part, right side of 0, so you can actually differentiate term by term in this interval. Okay, if your point is here, you include that in a closed interval by including in your bigger closed interval. Okay, so that way this series one can prove that is actually converging uniformly and absolutely and up to the next singular point. Okay, if I do not have any other singular point except 0, everywhere it is so. Otherwise 0 is the singular point. Suppose alpha 1 is the singular point. So here within this any closed interval, it is absolutely and uniformly converging. So I can do, this is the open. So 0 to alpha 1 is the open interval. So in any closed interval this series one can show that is converging uniformly and absolutely. So you can do term by term differentiation. Okay. So having assumed that part, you can differentiate this y dash of x as a term by term. So this you can write it like xk, you can put it and you can write n plus k. So if you do that, k is not an integer. Okay, k is not an integer or a natural number. So when you differentiate, everything will remain. So this index will never be 0 unless in the it is not like when k equals, when you usual power series, when you differentiate the power series, that constant part will go, n is running from only from 1 to infinity after differentiation, but here it is not so. So you have n plus k c n x power n plus k minus 1. Simply differentiate y x, y double dash will be n is from 0 to infinity. One more differentiation of this will give you n plus k minus 1 into c n x power n plus k minus 1. So this is what you have. Okay. So you substitute this 3 into the equation. So if you substitute this 2x, y double dash is this, n is from 0 to infinity, n plus k minus 1 c n x power n plus k minus 1 minus 2. This is actually when you differentiate twice, it will become 2. So minus 2 plus x plus 1 times y dash, that is n is from 0 to infinity n plus k c n x power n plus k minus 1. That is what is the second part. So and the remaining part is simply y, that is n is from 0 to infinity c n x power n plus k equal to 0. So this is what you after substituting. So what is the next step? So what you do, you just take it inside. So you will get n is from 0 to infinity. So 2 times n plus k minus 1 c n x power n plus k minus 1 plus this part n is from 0 to infinity n plus k c n x power n plus k plus sigma n is from 0 to infinity n plus k c n x power n plus k minus 1. So I expanded x into this and 1 into this plus sigma n is from 0 to infinity c n x power n plus k equal to 0. Okay. So what is the common terms here? N equal to everything's all the series are starting from 0 to infinity, but the common part is x power n plus k minus 1. Powers are x power n plus k minus 1 here, x power n plus k, here n plus k minus 1, here x power n plus k. So you convert this, you reduce this x power n plus k minus 1 into n plus k by changing this index. If I want n plus k minus 1 into n plus k, so that means n minus 1 I have to replace with n. Okay. So wherever n is there, you replace with n minus 1. So, in this for example here, okay, you can change the index, you know how to do it now. So, you do the same thing here, n equal to n minus, so this is running from 1 to infinity. So, 2 times n minus 1 plus k, n minus 1, so that means n minus 2 plus k, c n minus 1 x power n minus 1, sorry, n plus 1 you have to replace, right. N plus 1 if you replace, this is going to be n is from n plus 1 equal to 0, that is n equal to minus 1 to infinity, 2 n plus 1, okay, here 2 n plus 1, 2 n plus 1 will go. So, you have n plus k, c n plus 1, c n plus 1, x power in the place of n, n plus 1. So, this will become n plus k. So, this is already in the n powers of n plus k. So, you write as it is. So, you have n plus k, c n x power n plus k. Similarly, here. So, this you change the index, n equal to n plus 1 if you put, this will become x power n plus k. So, n equal to n plus 1. So, n plus 1 equal to 0. So, that means n equal to minus 1 to infinity, n plus 1 plus k, c n plus 1 x power n plus k, plus this is as it is because this is already in the powers of x power n plus k equal to 0. Okay. So, 0 to infinity it is common, and n equal to minus 1 here, n equal to minus 1 here, those are the only isolated terms. If you write separately them, you have n equal to minus 1 means 2 times n equal to minus 1, this is going to be k into k minus 1 into c 0, that is your n equal to minus 1 here, plus n equal to minus 1 you have k times c 0 equal to 0. So, this is this, or you just write this as this is separately, plus sigma n is from 0 to infinity c. Now, you can combine all these series, all the 4 series you can combine, that is c n. So, c n plus 1, c n plus 1 here. So, you have n plus 1 k, 1 plus k, okay. This is common, when you take common out. So, you have 2 times n plus k plus 1 times c n plus 1 into x power n plus k. So, that is also common. So, plus what else you have, n plus k plus 1. So, n plus k plus 1 times c n into x power n plus k. So, that is common in both places. So, you have x power n plus k which is equal to 0. Okay. So, this is what you have. So, this is, so now you have this this is one power series into n equal to minus 1, what you have is x power, I missed x power k minus 1. So, you can actually when you have this power series like this which is equal to 0 power series, you can actually make the coefficient 0. So, that will give you C naught, you do not want C naught to be 0. If C naught is 0, what happens? If C naught is 0, without loss of generality, you can always assume that C naught is 0 here, non-zero here. If C naught is 0, I can take one x out, and anyway k is unknown. So, once you take it, once C1 is 0, so you can write it will start from C1x plus C2x square and so on. So, you can take one x outside, you can write x power k plus 1 with the power series now starting with n equal to 0 to infinity, or you have C1 plus C2x plus C3x square and so on. So, that is like power series, same power series here. Instead of, if C naught is 0, you will have x power k plus 1, k is unknown, k plus 1 is also unknown. So, it does not matter. So, without loss of generality, you can assume that C1 is non-zero. So, because C1 is non-zero, you have this 2k into k minus 1 plus k has to be 0 by equating k power minus 1 coefficient, okay, 0. Next thing is k power n plus k, n is running from 0 to infinity, you can equate, that will give you the recurrence relation. So, this part will give you, so what happens this is equal to, so 2k square minus 2k plus 2k. So, that is going to be minus k equal to 0. So, that will give me k equal to 0 or 1 by 2. So I always choose k1 which is always big. What is big here? So bigger is root is this, smaller root is 0. So I always assume k1 is bigger than k2. So when they are same, I will choose like this. If they are complex, it does not matter, whichever you can choose as k1 and k2. So this is called indicial equation. Okay, so this is called indicial equation. So it has these roots. Okay, so when the root difference R1 minus R2 is non-zero and non-integer. This is the case 1. Case 1 we are dealing with. In this case, okay, so this is the case we are dealing. So if this is 0, okay, obviously the difference is R1 is non-zero and it is non-integer. Okay, if it is 0, it is one case. So we have 3 more cases. Okay, so we have R1 minus R2 is non-zero but integer, and case 3, because I have chosen R1 is always bigger, when it is non-zero it is a positive integer. So it is a positive integer, always positive integer. Okay, this is non-zero or rather non-integer, it is not an integer and not an integer, not a positive integer. Here also you can write not a positive integer because R1 is always chosen as big. Okay, not a positive integer. So this is one case, this is another case. Now you have a last case when R1 minus R2 is 0, that means roots are repeated. So this is the first case we are dealing, that is what we have seen, k1 minus k2 is 1 by 2. So this case belongs to this, whatever we are in this example belongs to the case 1. In this case it is relatively simple. So you will see that finding the solutions is relatively simple, because just by equating you will get two different, so you will be able to get two linearly independent solutions very easily. So what we did is we equate the coefficient of x power k minus 1, you got this indicial equation. If you do now all powers of x power n plus k, so powers of n plus k, coefficient of x power n plus k, n is from 0, 1, 2, 3 up to infinity. If you do, okay, is 0. Okay, coefficient of 0 for n is this. This will give me recurrence relation. It's called recurrence relation. Okay, so you will get a recurrence relation. What is that recurrence relation? This one. So n plus k plus 1, that is common. N plus k plus 1, that is common. So what you have is 2n plus k plus 1 into Cn plus 1 plus Cn, which has to be equal to 0. Where is it running from? Running from n is from 0, 1, 2 and so on. This is what you have, because n equal to k equal to, now you put k equal to fixed, k equal to 0 or half plus 1, 3 by 2 plus n is 0. So this will never be 0. Okay, this will always be, since n plus k plus 1 never be 0 for every k equal to, for every n 0, 1, 2, 3 and k is 0 or half. Okay, so this has to be your recurrence relation. You have 2n plus k plus 1 into Cn plus 1 plus Cn equal to 0 for n is 1, 0, 1, 2, 3 and so on. So this will determine your Cn plus 1. So put n equal to 0. So put n equal to 0 in the recurrence relation here. So you will get C1 equal to minus C0 divided by, put 2 times k plus 1. Okay, and put n equal to 1. If you put n equal to into this, you get C3, C2. C2 is n equal to 1. So, you have C2, that is minus C1 divided by 2 times n is 1. So, you have k plus 1, 2k plus 1 plus 1, and I already know what is this is going to be plus C0 divided by 2k plus 1 into 2k plus 1 plus 1. Okay. So, this is actually C0 divided by 2k plus 1 into 2k plus 3 and so on. So, n equal to 2, you will get C3 as minus C0 divided by 2k plus 1, 2k plus 3, and what is the next step? 2k plus 5 and so on. Okay. So, in general you will get, you can write the nth term if you like. Okay. So, you can go on getting like this. Now, what is k value? K is either 0 or half. So, start with in this case one, when the difference is non-integer, you put k equal to a bigger root k1, which is half. If you do this, what we gain is that C1, what happens to C1? C1 is minus C naught divided by 2 by 2. So, you have 2. So, C2 will be C0 divided by 2k plus 1. So, k equal to k1, which is half. So, it is going to be 2, it is going to be 4. Okay. So, similarly C3 will be minus C0 divided by, so 2, 4, 6 and so on, you get like this. So, this implies you go back and substitute. Now, you have got all most of your C's, C1, C2, C3, C0, okay, except C0 you got everything and you found 1k. 1k is, so you have that solution y1 as yx with k equal to half and cn's, corresponding cn's, okay, that is actually equal to x power k, which is half. So, we are writing, when you say x power half, x has to be positive, because this function, if when you are working with the equation with the x negative side, if you are working for the equation in the x negative side, when you get this x power k, when k is something, so when you write like this, you have to write mod x. Okay. Mod x means it works both for x positive and x negative. Okay. That is how your solution should be. So, if you are looking for x negative side, you should look for your solution in this form, mod x form, mod x power k. So, because you are working with x positive, your solution looks like this. Okay. So, anyway, so we are only working for x positive. So, you can say x power is simply x is positive, because x power half you can write, and then what is your power series? Power series starting from C0 plus C1. What is C1? You found here. So, minus C0 by 2 x plus C0 by 2 4 x square minus C0 divided by 2 4 6 x cube and so on. So, this is your first solution. This is equal to C0 is common, root x times 1 minus x by 2 plus x square by 2 4 minus x cube by 2 4 6 plus and so on. So, minimum 3 terms are there. So, you have, this is one solution. You can take C0 as 1, that is your first linearly independent solution, non-zero, clear, right. Now, you allow k equal to k2, which is 0. If you do this, what happens to your C1 from your recurrence relation? C1 is, if I put k equal to 0, so you have minus C naught. C2 will be minus C naught minus C1 divided by 2 plus 1, so 3 minus C1 divided by 3. So, this is going to be, so C naught divided by 1 3. Similarly, you can get C3 as minus C0 1 3 5 and so on. Okay. Put k equal to 0, k equal to 0 if you put 1 3 5. Okay. So, that is what you will get, so and so on. So, like this you can get all Cn's. So, if you do this, you can get, now you know what is your k and you know what is your C1, C2, C3. So, if you substitute y2 of x, yx at x equal to 0, at k equal to 0, okay, you have chosen this function at k equal to 0, which is x power k, k is 0, C0 which you could not find, C1 minus C0 plus C2, C2 is C0 plus C0 by 1 3, C1 into x, C2 into x square, C3 into 135 x cube and so on. Again here x power 0 is 1, C0 is common, you have 1 minus x plus x square by 1 3 minus x cube by 135 and so on. So, this is your second solution. If you choose C0 equal to 1, you will get a second linearly independent. So, you can see that y1 by y2 is actually two different things, this is not constant. So, that implies there are two linearly independent solutions, that implies y1 and y2 are y1x and y2x are linearly independent solutions, since y1 by y2 is not a constant. Okay. You can see that they are not same, they are not constant multiple of other. So, that implies the general solution is solution of the given equation is yx equal to C1 some arbitrary constant with y1 of x plus C2 y2 of x. What is y1 and y2? By considering your C1 as 1. Okay. Similarly, here you take it as 1. You choose, that is your C1 and C2. So, you have C1 and C2 are arbitrary constant. They are arbitrary constants. So, this is your general solution. Okay. So, this is your final general solution you got. So, this is your general solution you got, okay, with y1 is this and y2 is this one. Okay. So, you got this general solution of this equation when you have in the case 1. So, what is the case 1? You find the initial equation, you look for the solution in this form, and when you find the initial equation, the roots are difference of the roots r1 and r2 is non-zero and not a positive integer. So, we will see another example in the next video, where I consider an equation, you get the same case, but the difference they are distinct, but they are complex roots. So, that the difference is always imaginary. Two complex conjugate roots, that you take the difference, it will be imaginary numbers, that is not an integer, so positive integer. So, we will look into that example, and then we will see the other examples where these case 2, case 3, where the difference between the roots will be, one is not integer, they are distinct but integer, and they are same. So, that means the difference is 0. So, these two cases we will see in the next few videos.